Hello friends, myself Dr. Nandakumar Raubawale from College of Engineering Ambajurem is going to deal with numerical methods in mechanical engineering. This is our 16th lecture. In previous lecture, we have discussed about trapezoidal rule for integration of algebraic function or transcendental function. So today we are going to discuss multiple application of trapezoidal rule, then Simpson's one-third rule, and multiple application of Simpson's one-third rule. So in previous lecture, we have discussed about the application of trapezoidal rule. So now today we are going to discuss about multiple application of trapezoidal rule. Let us consider an example. This is the example. F of x is equal to 0.2 plus of 25x minus 200 x square plus 675 x cube minus 900 x to the power of 4 plus of 400 x to the power of 5. So this is the function which is to be integrated. So this is to be integrated between the limits of integration from a is equal to 0 to b is equal to 0.8. The true value of integral is also given. So true value of integral I is given as 1.640 533. So now this is to be integrated using multiple application of trapezoidal rule. So let us consider for solution number of intervals n is equal to 2 and step size h is equal to 0.4. So we want to divide this range 0 to 0.8 in two intervals. Each interval is of 0.4. H is equal to 0.4. So now, according to trapezoidal's rule, we have to divide it into two intervals. That is, first x naught value is equal to 0 we take, then x1 value is equal to 0.4 and x2 value is equal to 0.8. So this is to be taken. So for that, we need to write the formula for integration using trapezoidal rule, multiple application of trapezoidal rule. I equal to b minus a divided by 2 times n, and this is f of x0 plus of 2 into f of x1 plus of f of x2. So this is multiple application of trapezoidal rule. So we need to find out f of x0, f of x1 and f of x2. So we find these values here. So if we substitute f of x0 in this above function, x value as 0, so this complete term becomes only 0.2. So if we substitute x0 is equal to 0, the above equation, function f of x, so everywhere x is there, so everything becomes 0 and only 0.2 remains. So f of x0 is 0.2. x1 value, if we get x1 value is 0.4, f of x1, if we substitute here 0.4 everywhere, then the function value becomes 2.456, and if x2 value we substitute as 0.8, this function, then f of x2 becomes 0.232. So therefore, integration I can become b minus k, b value is 0.8, k value is 0, divided by n into n, number of intervals that we have considered is 2, in bracket f of x0 value is 0.2 plus of 2 into f of x1 value is 2.456 plus 0.232. Then this integration becomes no simplification. This is going to be 1.0688. 1.0688 is the value of integral. So this is the value of integral obtained using trapezoidal. Now if we want to find out error here, true error is equal to true value which is given in this problem. True value of integral which is given in this problem is 1.64053334. So this is true value 1.64053334 minus value which we have obtained by using trapezoidal rule. Multiple application of trapezoidal rule is 1.0688. So this true error becomes 57 1/7 percentage true error becomes this true error where the true value into 100. So this is 0.5717 where the true value is 1.640533. So this works out to be true error as 34%, 34.9%. Now, if we want to find out approximate error, PA given by minus 0.8 to the power of 3 divided by to 1 into 2 to the power of 2 into minus 6. So this is based on this equation. Approximate error PA is equal to minus B minus A to the power of 3 divided by 4 into n square. Here bar of double dash. So here B means 0.8, A means 0, N means 2. F double dash of zeta is minus 60 that we have calculated. So from this approximate error, which we get is point. So this is how we use multiple application of trapezoidal. So now let us consider another example for multiple application of trapezoidal rule. That is, we integrate a new function to validate integration 0 to 1 divided by 1 plus x dx using trapezoidal rule. Trapezoidal rule. So the true value of function is this is nothing but log to the base e, log 2 to the base e. And this true value of this is 16934 4 3147 3147. This is the true value of function. So now we will use it twice. So we will find this integral using single trapezoidal rule and single stage trapezoidal rule and multiple application of trapezoidal rule. Let us consider first h is equal to 0.5, n is equal to 2. Therefore, first value of x naught is say 0.0 or 0. Therefore, function f of x value, if we substitute x equal to 0, function f of x is nothing but is equal to 1 divided by 1 plus x. So when we substitute x equal to 0, so this function f of x naught becomes 1. Now, if one step if we take x1 value as 0.5, then f of x1 is equal to 1 divided by 1.5, means this therefore to be 0.667, and x2 value if we take second step as 1, then f of x2 becomes 0.5. F of x2 becomes 0.5. So now, applying trapezoidal rule, integral I can be written as b minus a f of x naught plus 2 f of x1 plus of f of x2 whole divided by 2 times here. So now, if we substitute the values of b and a, b is 1, a is 0, f of x naught is 1, in place of into f of x1 is 0.667 plus of f of x2 is 0.5 whole divided by 2 into n. N value is, on simplification, this integral works out to be 0.70835. So now here we can find out true error, because true value is known. So true error, relative true error can be given as true value 0.69347 minus the integral by the approximate value is 0.70835 divided by true value is again 0.69347 into 100. Then we get true value as true error as 0.69347 minus 0.70835 divided by 0.69 347 into 100. So this is 2%, 2.14%. Minus or plus, so it doesn't make. So error is 2.145%. So if you are dividing this total range 0 to 1 into two segments, n is equal to 2. So it is divided from 0 to 1, 0.5 and 1. So it is divided into two segments. Then we are going to get this much of error, true error as 2.145. Now let us divide it into four segments instead of two segments. Here what we have done here is we have divided it into two segments. Same problem we will solve by dividing this range 0 to 1 into four segments. Then again let us consider I is equal to integration 0 to 1 divided by 1 plus x dx. So here we consider now h is equal to 0.25, where the total range is divided into four segments. N is equal to 4. Then we take this as x naught is equal to 0. At that time, let us just say f of x is equal to 1 divided by 1 plus x. So function f of x, if we substitute x is equal to 0, so this value will become 1. If x1 is equal to, if we substitute 0.25, then f of x1 is equal to, it becomes 0.8. Then if x2 is equal to, if we take 0.5, step of 0.25, 0, 0.25, 0.5, so f of x2 then works out to be 0.6667, and x3 is equal to 0.75. Then f of x3 works out to be 0.5714, and if x4 is equal to 1, then f of x4 is equal to 0.5. So now if we apply trapezoidal rule, multiple application of trapezoidal rule to this, then we can write multiple application of trapezoidal rule equation like this: I is equal to b minus a f of x naught plus of 2 times f of x1 plus f of x2 plus of f of x3 and close this bracket plus of f of x4 last. So b minus a, b value is 1, a value is 0, whole divided by here it was 2n, 2n. So b minus a into f of x naught is 0.8 plus of 2 into f of x1 is 0.8. Here it was wrong. So this is 1. F of x naught is 1. 2. F of x1 is 0.8 plus f of x2 is 0.6667 plus f of x3 is 0.57 14, close this bracket, plus f of x4 value is 0.5 divided by 2 times n, 2 into here n value is taken as 4. So on simplification we get this as 0.6970. So this is integral obtained by multiple application, dividing this range 0 to 1 into 4 segments. So now if we want to find out true error is equal to, we can see here, this true error is equal to, true value which is given in this problem is, true value is 0.693147, 0.693147 minus approximate value which we obtained is 0.69. Whole divided by true value is 0.693147 into 100. So this works out as 0.693147 minus 0.6970 divided by 0.693147 into 100. So this error works out to be 0.55%. So if we compare previous error and this error, so earlier a true error was 2.14% and here this error is 0.55%. So this error is less as compared with this previous. So a reason is we have divided this segment into four, arranged into 4 segments, that is a small step size we have taken h is equal to 0.25. In previous case it was 0.5, so h was 0.5. So smaller is the segment, then more accurate answers we will get. So this multiple application of trapezoidal rule helps us to find out the more accurate results or more accurate integrals. So now coming to Simpson's one-third rule. So what happens in Simpson's one-third rule? Now let us consider one function. So this function follows this path. And we want to find out area below this function. So now we want to find out this area below this curve between these 2 points. So to find out area, we approximate this function with the help of a parabola. I assume that it is a parabola like this passing through these points. So then the area below parabola is calculated, and then is said that the area below the function f of x is equal to the area below parabola. So this is the parabola, and this is the function f of x. So function f of x is taken on y-axis, x is taken on x-axis. So the area which is below parabola is calculated and it is approximated to the function. So there is a larger error. So if instead of using a parabola, if a third order polynomial is taken, then better approximation can be obtained. So for example, we'll have another example. Let us consider this again, function, and we want to find out area below this function f of x between a to b. So now instead of approximating it to second order equation, if we are going to approximate it to the third order polynomial, the third order polynomial is approximated at that time. Third order polynomial is assumed to be passing like this. And area below this third order polynomial is calculated. So the accuracy of results compared to this second order polynomial, third order polynomial is better. Therefore, the Simpson's one-third rule is using third order polynomial. Simpson's one-third rule. I is equal to integration a to b f of x dx. which is approximately equal to the integration of function between a to b fn of x dx. If a and b are designated as if a and b are designated as x0 and x2 respectively, and f2 of x is represented by second order Lagrangian polynomial then integral becomes I is equal to integration from x0 to x2 x minus x1 x minus x2 divided by x0 minus x1 x0 minus x2 f of x0 plus x minus x0 x minus x1 x1 minus x0 x1 minus x2. Sorry, this is x minus x0 x minus x2 x1 minus x2 f of x1 plus of x minus x0 x minus x1 divided by x2 minus x0 x2 minus x1 f of x2 dx. After integration, the algebraic manipulations leads to the following equation, and that following equation is integral I is equal to approximately h by 3 function f of x naught plus 4 times f of x1 plus of f of x2. Close this bracket. So where for this case h is nothing but b minus a divided by 2. In previous case h was equal to b minus a divided by n. So here b minus a divided by 2 is taken as h. So for this is the Simpson's one-third rule. The Simpson's one-third rule can again be written as, it can be expressed I is equal to b minus a, that is nothing but h. B minus a, h can be written as b minus a, and this f of x naught plus 4 times f of x1 plus f of x2 whole divided by 6. This first term is known as width and second term is known as average height. So in this case also there is an error, and that error of integration which can be obtained by truncation error, which is known as truncation error. Truncation error which is given by e suffix t, which is minus 1 by 90 h to the power of 5 function fourth derivative zeta, or this can be written as minus b minus a to the power of 5 whole divided by 2880 fourth derivative of function zeta. So this is known as Simpson's one-third rule with a single stage, or simple Simpson's one-third rule. So now we will try to find out same function or integration of same function That is, example, f of x is equal to 0.2 plus 25x minus 200x square plus 675 x to the power of 3 minus 900 x to the power of 4 plus 400 x to the power of 5. So we want to integrate this in between interval a is equal to 0 to b is equal to 0.8. The exact integral is also known. That is, exact integral I is equal to 1.64053334. Now we want to use this. We want to simplify this function, integral of this function, using Simpson's one-third rule. So therefore, first we'll write the formula for integral using Simpson's one-third rule, which is equal to I is equal to b minus a f of x naught plus of 4 times f of x1 plus f of x2 whole divided by 6. So now we want to find out f of x naught, f of x1, f of x2. So first of all, x naught is equal to 0. Therefore, f of x naught, which is equal to 0.2. Then x1 value we take as 0.4. Then f of x1, which is equal to 2.456. And x2 value is equal to 0.8. Then f of x2 is equal to 0.232. So simplifying this, we get I is equal to b value is 0.8 minus k value is 0. Then f of x naught is 0.2 plus of 4 times f of x1 is 2.456 plus f of x2 is 0.232 whole divided by 6. So this is I is equal to integral we get as 1.3674 So this is the integral which we have obtained using Simpson's one-third rule, but true integral is here. The value of integral is given in the problem is 0.164053334. So true error we can find here as true error is equal to 1.64053334 minus approximate integral is 1.3674667 divided by true integral 1.6405334 into 100. On simplification, this true error works out to be 16.6%. So now, if we compare this true error with the previous errors, so this was the error using multiple application of trapezoidal rule. 34%. It was 34%. Now the error which we have obtained is only 16%. In a single step, if we use Simpson's one-third rule, error is approximately 50%. True error is 50%. So this is how we can say the error can be reduced using Simpson's one-third rule. So now if we want to find out approximate error in case of Simpson's one-third rule, so approximate error which is given here is given by formula approximate error minus b minus a to the power of 5 whole divided by 2880 f fourth order derivative of zeta. So now we know BA2880 only f fourth order of zeta we have to find out. So f fourth order zeta can be obtained by differentiating this function f of x 4 times. So if we differentiate it 4 times, then we get differentiation of this function as 2100 minus 21,600 plus of 48,000x. And integral of this has to be obtained. So on integration, this becomes 21,600 x plus of 48,000 x square divided by 2. So if we substitute limits of integration from 0 to 0.8, then this becomes, so integration of this is dx. So by substituting limits of integration in this becomes minus 2400. So here approximate error, if we substitute b minus a is 0.8 to the power of 5 minus and divided by 2880 into this minus 2400. So this works out to be 0.2730. Approximate error is 0.2730. So this, while finding this zeta to the f to the power of fourth of zeta, so what we are going to do is this function f of x, which is equal to 0.2 plus 25x minus 200 x square plus 675 x to the power of 3 minus 900 x to the power of 4 plus 400 x to the power of 5. So this has to be differentiated 4 times. So once we differentiate first time, this term becomes 0, then this term becomes 0, third time this term becomes 0, and fourth time this term becomes 0. So only differentiation of this is going to remain. So differentiation of this is going to remain, and that differentiation is going to become 21,600 minus, and this differentiation of 400x to the power of 5, fourth differentiation is going to become 48,000x. Again integration of that is going to become 21,600x 48,000x square divided by 2, and substituting limits of integration 0 and 0.8, then from this we get minus 2400. That is f fourth differentiation of zeta is minus 2400, and by substituting we get approximate error as 0.2730. So in next lecture we'll discuss about multiple application of Simpson's 1/3 rule and Simpson's 3/8 rule. Okay, thank you. We stop here.